Hey everyone, welcome to The Explainer. So, if you're gearing up for a competitive structural engineering exam, or, maybe you just need a rapid fire, high yield revision session for the IS 3370 Liquid Retaining Structures code, well, you've landed in the absolute right spot. Today, we're going to build your ultimate mental cheat sheet. We're stripping away all the fluff and zooming right in on the strict, non negotiable rules of water tank design. Let's get into it. Okay, let's dive into this. Here's our game plan for today. Anatomy of a water tank, concrete mix and materials, permissible stresses and cracking, reinforcement and detailing rules, and finally, movement and construction joints.
Starting off with Section 1, the anatomy of a water tank.
Now, to actually memorize these abstract AIS 3370 code provisions, we really need to visually anchor them to a physical structure first, right? Because if you can see the tank in your mind's eye, honestly, the maths just makes so much more sense. Take a look at this elevated INSEE-type tank. We've got the main top container holding the water, and that's supported by horizontal ring beams that are actively fighting off that massive outward hoop tension. And then right below all that is the staging, basically the system of vertical columns and braces. Oh, and here's a crucial tip to remember. Because these structures are so incredibly top-heavy, the AIS 1893 seismic rules actually treat them as a two-mass model. That means they account separately for the impulsive mass, that's the water moving with the tank, and the convective mass, which is the sloshing waves.
All right, moving on to a classic exam concept. You really need to know how the base connection of that cylindrical wall totally changes the internal forces. Think about it. If the base is flexible or sliding, your maximum hoop tension is right down there at the bottom, and you've got zero bending moment. But if that base is fixed or restrained, well, it acts just like a cantilever. Suddenly, a bending moment develops at the base, and your maximum hoop tension actually shifts upwards. It moves to about 0.6 to 0.7 times the height from the top. Seriously, keep that upward shift in mind. It's a huge detail.
Okay, moving right along to Section 2, concrete mix and materials. So let's see how all of this builds into the actual physical materials we use. Water tanks face what the code calls a severe exposure condition, and that means the rules are incredibly strict about what actually gets dumped into the concrete mixer. You're going to want to take a mental snapshot of this table right here. These are your first principles for the mix. Just notice how the requirements relentlessly tighten up. So, for plain concrete, you need a minimum of M20 grade with 250 kilograms per cubic meter of cement and a max water-to-cement ratio of 0.50. Step it up to reinforced concrete or RC, and boom, it jumps to M30, 320 kilograms of cement, and a tighter 0.45 ratio. And for pre-stressed, it goes all the way to M40 grade, 360 kilograms of cement, and a super tight 0.40 ratio.
But hey, watch out for this exception right here. Competitive exams literally love testing exceptions to the standard M30 rule. You actually are permitted to use M25 grade for reinforced concrete, but only for small capacity tanks up to 50 cubic meters. And, wait for it, the real kicker is that they absolutely cannot be in coastal areas. Do not let that detail slip past you. All right, let's test your recall right this second with a direct mock exam question. Do you know which specific aggregates are totally 100% banned by the IS code for liquid retaining faces? Well, if you guessed porous aggregates, you nailed it. Under no circumstances can you use slag, crushed over burnt brick or tile, bloated clay, or sintered fly ash. And honestly, it makes total logical sense, right? Using porous, sponge-like materials on a structure whose literally only job is to stay liquid tight, yeah, that completely defeats the purpose.
All right, let's pivot to Section 3, permissible stresses and cracking.
So let's shift gears and look at the structural math, the critical limits that tell us exactly how to handle water pressure, temperature stresses, and the ever-present risk of cracking. Historically, IS 3370 relied really heavily on the working stress method, or WSM, which strictly limits stresses to prevent cracks from ever forming in the first place. But today, the limit state method, or LSM, is highly utilized. LSM allows some higher stresses, but it tightly, and I mean empirically, controls the calculated surface crack width. Now, what's fascinating here is that under LSM, liquid load is treated with a load factor of 1.5, so it essentially acts as a highly controlled dead load, simply because its maximum volume is capped by the overflow pipe. Because we're trying so hard to control those cracks, the allowable stresses in the steel reinforcement are actually much lower here than in your standard IS 456 building codes. Check this out. On the liquid retaining face, mild steel is strictly limited to 115 newtons per square millimeter, and HYSD bars are capped at 130. And even on the dry face, away from the liquid, HYSD is still maxed out at 150. Basically, we are deliberately understressing the steel so the surrounding concrete doesn't stretch and crack. Make sense?
So the absolutely crucial takeaway here is this exact number, 0.2 millimeters. Listen up. Under the limit state method, for standard severe exposure conditions in a liquid retaining structure, the maximum calculated surface crack width must never, ever exceed 0.2 millimeters. Seriously, etch that number right into your brain.
But it actually goes a bit deeper than that, depending on the structure's tightness class. Class 1, where maybe a small leak or a little surface stain is okay, holds steady at that 0.2 millimeter limit. Then you have Class 2, where appearance really matters and we only want minimal leaks. That requires 0.2 millimeters with a liner, or it drops down to a stricter 0.1 millimeter limit. And then there's Class 3. This is where absolutely zero leakage is tolerated. Class 3 demands a 0.1 millimeter crack limit, and it has to come with a guaranteed 50 millimeter compression zone inside the concrete section itself. All right, on to Section 4, reinforcement and detailing rules. Now we're moving from the pure math into actual physical placement on the site. Detailing rules are exactly where points are so easily lost on exams if you start mixing up your dimensions. Look at this number, 45 millimeters. This is the absolute minimum nominal clear cover required for all reinforcement on the liquid retaining face. Not 25, not 30, it is firmly 45 millimeters. That is your baseline to protect that steel from the water. To fight back against shrinkage and temperature variations, we need minimum reinforcement, and it actually operates on a sliding scale. Think of it like this. For thin members up to 100 millimeters thick, you need 0.3% of the concrete area. As that thickness grows from 100 up to 450 millimeters, the requirement drops linearly down to 0.2%. And for anything massive, talking over 450 millimeters thick, it just stays flat at 0.2%.
Oh, and here is a totally non-negotiable detailing rule you just have to remember. If your concrete wall or slab thickness is 200 millimeters or greater, you cannot, I repeat, cannot just bunch all your steel in the middle. The reinforcement absolutely must be placed in 2 separate layers, with one near each face. This is critical to effectively distribute those stresses and keep surface cracking under control. Almost there. Section 5, movement and construction joints.
Finally, let's talk about joints. As you know, concrete isn't just the static block. It shrinks as it dries out, and it expands when the temperature rises. It needs room to breathe and flex. If we don't control exactly where it moves, well, it's going to crack right where we don't want it to. Now, what's really interesting about this slide is the visual definition of a contraction joint. Look closely. It is a deliberate discontinuity in the concrete, often with a water bar placed right in the center, but there is absolutely no initial gap between the concrete faces. None. It's poured completely flush, and it's intended to only open up when the concrete shrinks and pulls away from the joint. This is a classic exam trap, guys. Do not confuse this with an expansion joint.
Now compare that to expansion joints. Right here, we physically must have an initial gap, and it's filled with a joint filler. This deliberate gap exists to accommodate the actual physical growth of the concrete when it heats up. And just below that, you'll see sliding joints. These have complete discontinuity, often using a rubber pad, which allows a wall to literally slide over a floor with minimal restraint. It's brilliant because it completely prevents those dangerous bending moments at the base.
And our last joint type, temporary open joints. Honestly, this is such a clever construction trick. A gap is intentionally left open between the concrete pores. You just wait, letting the early age heat of hydration and all that initial drying shrinkage dissipate and pull the concrete apart naturally. Only then, right before the tank actually goes into service, do you fill that gap with concrete or mortar. It basically bleeds off massive amounts of internal stress before the tank ever holds a single drop of water. So what does this all mean for your exam? Well, that brings us to our final revision test to close out this explainer. Here we go. What is the absolute maximum crack width allowed for a tightness class 3 structure? And what specific structural guarantee absolutely must accompany it? Think about it for a second. If you instantly recalled the 0.1 millimeter limit and the mandatory 50 millimeter compression zone, fantastic. Your mental cheat sheet is solid. Just keep reviewing these numbers, visualize the physical structures, and you're going to absolutely master IS 3370. Thanks for joining me, and good luck with your studying.